Thanks very much. So this year I'm going to be talking about helicopters and rocket planes, which is really just a short summary of some of the crazier things we've been doing over the last year and that we're preparing to do over the next year in the world of open source autopilots. There's massive amounts of development going on in free software autopilots at the moment, and I just had to pick a few little bits out of it that I thought might have been of interest. So where I got started in open autopilots was with a competition. I was at the local hackerspace in Canberra, Make Hack Void. There's a number of Make Hack Void members here, I believe, today. And it was my first meeting at Make Hack Void, and there was a little huddle of people in the corner. And they were chatting about, model aircraft and trying to, drop bottles on people, and that sounded interesting. So I walked up to the group and asked if they wanted a software engineer, somebody who could perhaps, write some of the software for what they were planning to do. So what they were working towards was the Outback Challenge. And the Outback Challenge is a robotics competition which is held every 2 years in Queensland and is trying to push the boundaries of amateur autopilots. And challenges like this are really a wonderful way to push things along. So the challenge at the time was to fly a plane about a total distance of around 70 kilometres or so and use an onboard camera to find a lost bushwalker, and then once you've found them, automatically drop them a rescue package which was represented by a water bottle, and then fly back and automatically land. So auto takeoff, auto search, automatic image recognition, fly back and auto land. So that ran for 7 years before finally teams completed it. So in the 2014 challenge, nobody had completed the challenge before 2014. We won on points in 2012. We didn't actually complete the challenge. Then in 2014, we had several teams in 1 year complete the challenge. And our team was lucky enough to get the closest hit to Outback Joe, and without actually hitting him, which is important, and managed to win the prize. So once that was completed, the organisers said that if anyone completed the challenge, they'd try to make it harder. And the challenge for this year is that next challenge, where they're trying to make it harder, because it's flying 70 kilometres unattended and recognising and dropping things is all too easy these days. That's now an out-of-the-box experience where you can just download an autopilot that does that for you. So now we need to make it a bit harder, and they're particularly pushing an aspect of autonomous flight, vertical takeoff and landing. Because one of the problems with the solutions that all of the teams came up with last time is they all need a runway. And as yet, we don't have legislation that requires that bushwalkers get lost within 5 kilometres of runways. So they realised that perhaps some ability to take off and land vertically would actually be quite important. So they came up with this new concept called the Outback Challenge Medical Rescue. And you can see it on the picture there. The idea is you take off at one point where the little yellow aircraft is sitting there in the top left corner, and you need to fly a total distance of around 60 kilometres, so 30 kilometres to a destination and 30 kilometres to get back. This time round, you know roughly what the destination is, and you know roughly what the flight path is. And the backstory is that Outback Joe has got some medical condition where he needs some analysis of a blood sample urgently, and all the roads are blocked, and for some reason, nobody can get to him. The idea is that a UAV goes out and picks up a blood sample off Outback Joe and brings it back. And you're not allowed to collect the blood sample using a propeller. You have to actually land more than 30 metres away from Joe. If you get within 30 metres, then you're instantly disqualified. So a lot of the challenges around airframes that can do vertical takeoff and landing. There also is, you've got to pick a landing site. In the last challenge, the takeoff and landing was happening within a couple of 100 metres of where the operators of the aircraft were sitting. So we saw the aircraft take off and we see the aircraft land. And any of you who have had anything to do with aviation will know the takeoff and the landing is really the hard bit. So this time, the landing and the takeoff are happening 30 kilometres away. Right? So you've got a communication link, you've got a challenge to keep communication up to that vehicle 30 kilometres away. And you've got to, or line of sight, it'll be less than 30 kilometres, there's 30 kilometres, via the path. But you've got to keep that communication link up, and then it's got to autonomously land, and it has to be a vertical landing. There is no runway. And you're not even told exactly where, a good landing spot is. You've got to use image recognition and work out a landing spot, and then land at that remote site, and then shut down completely. And that's difficult. You have to turn off any motors, right? So you've got petrol motors that are shut down. And then Joe walks up and puts the blood sample on the vehicle and presses a button, and 1 minute after the button press, you're allowed to start up the motors. Start it up too early and you'll collect a second blood sample if Joe is still standing too close. So they press the button, the blood sample gets loaded, and then it's got to fire up its motors and take off vertically, and then fly back via the flight path and come back and land at the original site. So the computer vision task this time is in many ways easier because you know roughly where Joe is, so really there's only a few images you need just to find a suitable landing point. And so you know the position of Joe to within 100 metres. But you've got to then try to land accurately on a good spot without, landing on top of a bush or a tree or something like that. But a lot of it's to do with the vertical takeoff and landing side of things. So how do you do this vertical takeoff and landing? And as soon as the rules came out, we realised there were two really obvious solutions. One is helicopters, and the other would be a quad plane. So I'm going to describe a little bit about each of those and what we've been doing with them. Canberra UAV, we're a group of amateurs and sort of enthusiasts, crazy people as we're known by the other people who fly model aircraft around Canberra. And so we decided that we wouldn't just bet on one of these, we'd do both. Right? So we'd learn all about helicopters and we'd learn all about quad planes, we'd build both and fly both. And I mentioned there's a bit of a communications problem where you've got to have constant communication to your vehicle, even though it might be on the ground 15 kilometres away. And that is a challenge for radio technology over unknown terrain. So the solution is that you have two aircraft. So you actually have a second aircraft acting as a radio relay. So quite likely we'll end up with both a helicopter and a quad plane flying in this mission, one acting as a radio relay for the other. So they have very different autopilot needs, helicopters and quad planes. So I'm going to, the key is they both offer long range and high speed. Roughly speaking, you need to fly for 100 kilometres an hour for around 45, 50 minutes and take off and land vertically, which makes it very difficult to do a pure electric aircraft to do this. The energy density of batteries really just isn't up to it. You might be able to squeak it in, but not with the sort of, rough and ready engineering that characterises Canberra UAV, where, the sticky tape and hot glue and zip ties are, a lot of our kit. It would have to be a very refined aircraft to try to do it pure electric. So I'll talk a bit about what we've been doing with helicopters first. So helicopters are hard. They're basically flying vibration generators with rotating swords at the top. And the vibration in particular are, absolutely mad, really mad vibrations. And that's a problem for an autopilot that's trying to do this perfect control. And a lot of helicopters are really aimed at 3D flight, incredible aerobatics. Who's seen the sort of aerobatics that model helicopters can do? Yeah, if you haven't, just do some YouTubing, and it's just amazing to see exactly what people manage to do with model helicopters. So they're difficult to scale up, particularly as the smaller ones tend to be electric and the vibrations aren't quite so crazy. As you scale up to, say, two-stroke petrol engines, then the vibration goes up. And you scale up again, you might go do a large four-stroke engine. The vibrations get really insane. And so, of course, we're aiming for that higher size, where we've got, a 50cc four-stroke engine. and nearly 2 metres of blade length, blade diameter, and a copter that'll probably weigh in at about sort of 12 to 14 kilograms when it's got all its payload on it. So that's towards the larger end of model helicopters. And so this is a picture of one of our prototype helicopters. That's a JS90, which was originally a nitro helicopter, but we've replaced the engine with a 15cc petrol engine because the petrol gives a much higher degree of efficiency, and we wanted that 100 kilometres an hour for an hour type benchmark. And helicopters can do that. They can carry significant payloads over long distances really quite fast. They are incredible machines. So helicopters are hard, but they're also very rewarding. They are extremely efficient at VTOL. And basically, it's the large disk area. Larger propellers are more efficient. And helicopters are the biggest propellers, right? Enormous propellers. That gains an awful lot in efficiency. And once they're flying a fast-forward flight, they have this interesting property where their efficiency can actually increase as they speed up. Hovering is actually harder for a helicopter and can use more fuel than, moderate forward flight. Once eventually drag catches up with you and really fast forward flight, the efficiency drops again. But it's a much flatter curve than most other types of aircraft. Petrol, you need a petrol helicopter for really high energy density to be able to do long range at high speed. They have amazingly high precision control. And so they can cause the controls on a helicopter can cause the vehicle to sort of rotate at 720 degrees a second or more. So just flip, flip, flip like that, as you see in the 3D videos. And that gives them amazing degrees of control in high wind. Massive gusts of wind, they can handle that really well, which is very attractive because in the rules of the Outback Challenge, they continue to run the competition if the average ground speed at the point of takeoff is below 25 knots. So they only call a halt to the competition if the average goes above 25 knots. Now, 25 knots for a model aircraft is a heck of a lot of wind. In the last competition, the limit was 20 knots. They said they wouldn't fly if the average was above 20 knots. Both times we flew in the competition, we had more than 20 knots. And even though that was the rule, because that was 20 knots on the ground at the time of takeoff. Once you get into the air and you're flying over the field, the wind starts coming up. So it is a windy area of the world, or it can be, particularly if you're flying in the afternoon. And so being able to handle really high wind is a very attractive feature of helicopters. Okay, so here's a video of our larger helicopter. This is a GX9. So this is a 900 class helicopter with a 50cc petrol motor. And you're probably getting a bit of a sense from the sound there, and it's a bit hard to see the picture of this. I probably should have been zoomed in a little more. But it is vibrating like mad, absolutely vibrating like mad. And it is being stabilised by a small flight controller, and it's just hovering around. But this is what they look like, and the idea is that this will fly 30 kilometres away, and then land, and then shut itself down completely. This one's got a starter motor to auto start, so we can press a button and it starts the motor, which is really attractive, of course. That's all built in, and they're quite amazing machines. But things can also go wrong. So if you have a look at this little graph on the right here, it tells a story about controlling helicopters. So, we have our little autopilot on board, and we can tell it to capture all of the sensor data at full rate. So that means it's capturing the primary accelerometer at 1 kilohertz, and it's capturing the secondary accelerometer at 1600 hertz. So that's a lot of data it captures. And then we can run FFTs over that. So this is the result of an FFT of flying that JS90 that I showed you before, the close-up photo. And the interesting thing is where these peaks are. The horizontal axis here is in hertz, and if you can't see it, the first little number there says 100 hertz, so that first peak is around, 23, 24 hertz or so. And that is the rotation speed, that's basically the period of rotation of the rotor blade. So it generates this oscillation around 23 hertz or so. And then the second peak there is the blade passage frequency. So that's the frequency at which the individual, there's two blades, are passing through the air. So it's double because there's two blades. The control frequency which you're aiming for to actually control these things is typically around 20 hertz. Now, that gives a bit of a problem. When you've got massive oscillations at 23 hertz and you're trying to control something at 20 hertz, then you can very easily get into massive control problems. So isolation of the IMU is critical, but if you isolate it at 23 hertz to get rid of that noise, then you're also isolating it at your control frequency. And you need the data at the control frequency in order to be able to control it. Because if you get rid of the data at your own control frequency, you can't control it. So this is where helicopters get really hard, particularly as they scale up. The smaller helicopters, the frequency and the rotation rate of the blades is much higher. That might be 30, 40 hertz, giving you a bit of a gap between your control frequency and your the vibration. So what problems does this cause? So this is a graph of a flight which was less than successful. What we're seeing here, now again the numbers might be a little bit small, so on the left-hand axis we're seeing the amplitude of the red line is the amplitude of the accelerometer, right? Just our vertical accelerometer, just one axis of it. And the scale there, the first number past the midpoint is 100 meters per second, so 10G. And you can see there that there's this band. On the left-hand side, it's flying beautifully, right? The left-hand side there, really nice flight, beautifully stable, lovely helicopter. And you can see there that peak to peak, it's generating about 6G worth of vibration, right? So that's fairly normal for a helicopter. So 6G is actually a lot of force, right? And that's just in normal, stable flight, vibrating up and down at 6G. And then we see this phase of the graph in the middle there, where it's a little more than 6G. And to get you an idea of the scale, so after 100 comes 200, then 300. Our accelerometers, we've got, in this particular vehicle, we had two sets of accelerometers, an MPU 6000 and an LSM 303D. Both of them are linear up to a maximum of 16G, right? So 160 meters per second, and it starts going bad. The MPU 6000 actually clips at 16G. The LSM 303D just starts going non-linear above 16G, and then it absolutely clips at 24G. And you may notice there's this little part of the graph there which you never want to see in a flight log of a model aircraft, which is a very flat top. And you can guess what number that is. That's 24G. And so the aircraft, in a space of a couple of seconds, went from 6G of vibration up to saturated 24G, and probably extrapolating it was more like 30, 35G, something like that. Peak to peak, it's more like 70G. So that's a lot of vibration. So the cause of this was a very small change in the tuning on the pitch controller, and that's what those blue and yellow and green lines are. They're the control inputs and control outputs of the tilt of the swash plate. All right, the swash plate is the part of the helicopter that twists the blades to allow it to control its attitude. And there's three little servos on the swash plate, what's called CPPM mixing, where you've got two servos that really control the roll, and one servo that controls the pitch for moving the helicopter, pitching forward or pitching up. And then the three of them combine to give what's called the collective, which is basically how much it climbs or descends, how much lift or thrust downwards it gives. And we just did a tiny tweak, just wafer thin, as they say in Monty Python, a little tiny tweak to the pitch control. And suddenly we got catastrophic feedback in the control algorithms. And the pitch controller went out of control and started feeding back on itself. right? Because the oscillation is around the same frequency as our control frequencies. And so when it saw a movement this way, it pushed back the other way, and we ended up getting a build-up. And the whole helicopter just was shaking like mad. Now what happens is that at that point, we're running a Kalman filter, which is basically a sensor fusion technique for taking all of the different sensors, the GPS and accelerometers and gyros and compass and barometer and laser rangefinder and all these different sensors, and fusing them all together and trying to get the state of the vehicle, where it is and what its attitude is, right? And how, all its velocity, etc. And the Kalman filter basically lost the plot, right? And it no longer knew which way was up. And once a helicopter doesn't know which way is up, it very quickly tries to go to where it thinks it wants to go, but it actually isn't going there. And there was an inconveniently placed tree, which wasn't where the helicopter thought, it thought it was over here, and it was actually over near the tree, and bang, all over in a couple of seconds. And we actually dropped the tuning factor down. You can see that it did recover in terms of oscillation, but by that stage, it had lost the plot as far as the attitude of the aircraft was no longer controllable. And when they go wrong, they go very badly wrong. But when they go right, they're wonderful. So here's one going right. This is the JS-90 helicopter doing an automatic takeoff and automatic flight, so a fully autonomous mission. So this is running our little autopilot software. It takes off like that. You can see a lot of vibration still. And then once it's done this automatic takeoff, it then transitions to forward flight and starts off around a fully autonomous mission. And this particular mission, it got up to around 100 kilometers an hour, and there was enough fuel on board for around half an hour's flight or so. There it is, heading off on its mission and slowly speeding up as we command it. So when they work well, they do work amazingly well. But there are challenges with the controlling of helicopters, principally because of the lack of gap between the natural oscillation frequency and the control frequencies. All right, so there are other solutions to vertical takeoff and landing. And as I mentioned, we decided that we would investigate both. And we didn't know which would be the best for what we're doing. Plus, we like to have fun with building crazy aircraft. So we decided that it would be fun to actually build both helicopters and quadplanes. So you can see here the idea behind a quadplane. There's two quadplanes that we've built. So the bottom one was the one we first built, which is based on a venerable aircraft, a design from back in the 1950s, I think, called a Senior Telemaster. And it's sort of balsa and covering. And what we've done is we've taken this basic aircraft, which is a petrol aircraft. It's got a 15cc petrol motor in the front. A really nicely, easy to fly aircraft. There's the catchphrase of the manufacturer is, nothing flies like a Telemaster. They fly really beautifully. So we stuffed all that up. And we stuck 4 quadcopter motors on this thing, on some aluminium square section tube there, strapped underneath the wing. Then we stuck a whole bunch of batteries in it, lots of heavy batteries in it. And that thing was able to then take off vertically as a quadcopter and then transition to forward flight by starting the petrol motor, right, which allows it to have the vertical takeoff capabilities of a quadcopter, but the speed and endurance of a fixed wing. And some people describe them as being like splades or sporks, where they're sort of, not really a great knife or fork or spoon, but able to do all of the jobs. And they're a bit like that. So helicopters are a much more elegant solution to the problem. But in many ways, quadplanes are simpler. And from a control point of view, because when they're in forward flight, it's relatively easy. And flying them vertically, it's just a quadcopter. There is this transition phase where they're sort of halfway between being a quadcopter and a plane. And we initially expected that might be hard. And it turns out it's absolutely trivial. And so the very first time we tried it, we actually just fitted 2 flight controllers. So we had 2 autopilots in that yellow plane, and we had 2 pilots on the ground that had 2 RC controls, one of them controlling the fixed wing and the other one controlling the quadcopter autopilot. And what happened was the quadcopter person just said, take up, and then just puts it into hover, right? And then tells the guy on the controls for the fixed wing to say, okay, start advancing the throttle and flying. And he started advancing the throttle and it flew forward and went off beautifully. And, well, that was easy. It really was amazingly trivial. So then, of course, the task is to automate it. And we had a very strong motivation for automating it because we actually crashed that yellow one. And the reason we crashed it was essentially there were 3 pilots. There was one person holding the transmitter for the quadcopter part. There was one person holding the transmitter for the fixed wing part. And then there was me on the keyboard coordinating, right, and giving all the data and saying, we're going to do this. And so before each flight, we'd have a coordination session, you know, you're going to do this, then we're going to do that, etc. And on the very last flight of this plane, it was a human mistake in the coordination between the 3 pilots. Having 3 pilots in one aircraft is hard. And the wrong button was pressed, and it was hovering at about 10 metres, and the quadcopter turned off at 0 speed. And the plane doesn't fly very well when it's just sort of sitting there with no motors vertically. You can put the forward throttle on all you like, but you're not going to suddenly accelerate up, not at a height of 10 metres. You can't recover. And so, of course, it tumbled into the ground, and you know, it now rests with all the other models that we've destroyed over the years. So the top one we haven't destroyed yet. It's a smaller one. And it has just a single autopilot that completely automates the transition between these 2 flight modes. So now just one person can flick a mode, and we made it so there is no button that causes the aircraft to just tumble into the ground and crash. You know, whatever you do, if you just hovering there and you say flick to forward flight without any quadcopter, it will actually keep the quadcopter there and automatically hold it. If you put the transmitter down, it'll just sit there waiting for the next command, right? Until you start saying, okay, now start accelerating forward, and it won't. It'll slowly decrease the quadcopter motors as it gains airspeed and gains lift from the fixed wing. So it's much more foolproof, removing the human mistake element. Quad planes are somewhat difficult to scale, but first of all, I want to talk a bit about why quad planes make sense, and that's really summarised by this graph. And this is a graph from a real flight of that quad plane, the top one on the previous slide, which was the electric foam quad plane. And you can see here there's 2 lines. There's the red line, which is the current in amps. This is an electric quad plane, pure electric, so one battery is supplying both the forward motor and the vertical motors. And then the green line is the airspeed. So at low airspeed, it's hovering, and at higher airspeeds, it's in forward flight. And what you can see is the red line is on average an awful lot lower once you're moving forward, because in fixed wing flight, it's really efficient. And it's about 1/3 of the current. Even though you're going much faster, right, you're getting the job done, you're only using about 1/3 of the current. And that basically, why is that? Well, wings work, right? Wings really are a very efficient way of getting along, which is why they're so popular in aircraft. So, towards the end of the flight, you can see there where it goes to low speed again, it transitions back to vertical flying, and suddenly the current leaps up, right? But then you need to multiply this graph by an extra multiplier. In forward flight, you can use a petrol engine, right? Because the control speed of petrol engines is low, but you don't need high control speed for the forward motor. And that gives you another like 20 or 30 times of efficiency, typically, as far as energy density is concerned. So the batteries in our quad plane, for our larger quad plane, might give you a couple of minutes of vertical flight. And that's with 4 or 5 kilos of batteries in a 19-kilogram plane. The petrol, which might be only a litre and a half, will give you maybe an hour at 100 kilometres an hour, right? So you get this massive efficiency in forward flight. So let's have a look at what that looks like. This is our little foam test quad plane doing this is a fully autonomous mission, so auto takeoff, automatic transition to forward flight, and then an automatic mission, then come back and automatic landing at the end. There it goes, a little bit unstable at the first. That's what quad planes are a bit awkward when they're getting off the ground. And now it's quite stable once it's in the air, and then it'll start transitioning to forward flight. Now notice it actually goes backwards for a second, and that's because it pitches up. This version of the code pitched up to try to climb, and that causes the quad motors to make it go backwards for a second or so. That's actually been fixed in a later version of the code. And there it is, heading off on its autonomous mission, and then at the end of that it'll come back and do an automatic landing and come back and land at the airfield. So one button, fully autonomous VTOL missions, which is great. It's really nice to see that working. We just got to scale up to a much larger size. So enough on quad planes. Now I'm going to talk about something totally different. I promised you rockets, right? I said helicopters and rocket planes. And one of the problems with conferences is you've got to put in the description of your talk a very long time in advance. And I was hoping that this mission that I'm going to be talking about now would have been completed, and we would have had the video of the resulting crater in the ground to show you. Unfortunately, that video hasn't been produced yet. So I'm just going to talk about what we have done with this rocket plane mission. So what you see there, that very patriotic British aircraft, is from the Register Special Projects Division. So the Register is a wonderful IT site with controversial approach to reporting IT news. And they also have this Special Projects Division, which they did, like, for example, the Paris project, which was the first paper airplane in space. And their project for the last few years has been this LOAN project, which is the Low Orbit Helium Assisted Navigator project. And the idea is that that plane will be taken up to 20 kilometres in a balloon and then fire a rocket and get up to Mach 2. And then when the rocket expires, then an autopilot will take over and bring it back and land it at Spaceport, USA. So it's a really ambitious mission. And it's a 3D printed aircraft, which is unusual. So lots of unusual things. It's hard enough making a good aircraft out of normal materials, but to actually make one that can handle, Mach 2 with 3D printing is really quite a challenge. So this is the basic idea of the mission here. And so this is their pictograph of it. So the phase one, you have a weather balloon that takes that plane on this great big metal scaffolding up to a height of 20 kilometres, right? And the idea is the balloon will burst just above 20 kilometres. So it takes it all up. It's got on board, it's got a little Raspberry Pi, right, running Raspbian on board, and it's got our little autopilot, one of these autopilots here, a little Pixhawk autopilot running ArduPilot, and it's got a bunch of radio gear, again running firmware that we've developed. And when the balloon, so phase two begins when it fires off this rocket. So inside the tube part of the plane there is a rocket. And that rocket gives it about an 8-second burn time and accelerates the aircraft up to, they're hoping to get to around Mach 2. The autopilot's job is on the way up, it's supposed to just wiggle its servos to stop them freezing up, because it gets pretty cold up at 20 kilometres, right? That's one of the coldest points of the atmosphere. And so it's wiggling its servos to sort of get up there, and then it's supposed to hold very still when the rocket goes off, because it really doesn't have a chance of controlling it in the rocket phase of the flight. So the idea is don't even try and control it and just hope that it goes straight. There's a lot of hoping in this mission. So it'll probably lose GPS at the time when it goes into rocket phase, because it'll be past the limits in what the U-blocks will do as far as velocity. And so then after the rocket burns out and it's had a few seconds to start slowing down a little bit, the autopilot takes over and hopefully flies it all the way back to the base and lands neatly at Spaceport, USA. So there are some challenges to this as far as the autopilot's concerned, but I'm always up for a crazy challenge in autopilot development. So the easy bits are sort of the, wiggling servos during the ascent. We've added a special, wiggle servos mode, while waiting for the ascent. And then it's got a very simple little bit of code that just looks at the accelerometer to detect the rocket acceleration, and as soon as it sees that massive acceleration, just to lock the servos in place and hold them still, and while it sort of prays that it's going to survive this, that the 3D printed plane can actually handle that degree of acceleration. The interesting part of it is the fact that this flight will be its first flight. Normally, when you're building model aircraft, how many of you have built and flown model aircraft at all? Quite a few. Okay. So you know that the first flight is rarely perfect, especially the first flight of such an ambitious aircraft. And you've got to get your rates right, and you've got to get all your tuning parameters, and you might need to shift the C of G a little bit and trim the aircraft. Well, this thing's going to be at 20 kilometres flying at Mach 2 in very little air. And the picture that comes to mind for me, if you're a fan of The Hitchhiker's Guide to the Galaxy, you may remember the infinite improbability drive. And there was a whale that popped into existence above a planet. And the whale pops into existence, and it then has this philosophical discussion with itself where it sort of sees the ground and, think, oh, will it be my friend? And then it sort of discovers, oh, I've got these flipper things. I can flip them and they do things, right? So that's what the plane's going to be like. It's never flown before. It doesn't know its tuning factors. So we added the ability we've got this auto-tune mode, which is normally under pilot control, where you fly it around and it learns how to fly. So the plane needs to learn how to fly on the way down through the atmosphere. And hopefully it learns enough about the theory of flight and, how to control itself on the way down that it's able to then, neatly come in for the landing. There is, however, a slight issue that knowing the altitude to land at is going to be somewhat difficult because it just has a barometer on board for altitude, and barometers tend to get a little bit upset when you drop them down to minus 50 degrees C, and you have them going for a couple of hours in a weather balloon and things, and so it's supposed to then know its height. And we're hoping that it will try and land, on the runway, but it might decide to land 10 metres under it or, 10 metres above it or something, and that could get interesting. Anyway, so we need to do lots of test flights, so we can't test flight the actual plane. This is like, one use, so we just test flight all the avionics on board, the bits of electronics and the servos and the autopilot. So we worked with the Edge team in the US that works on high-altitude ballooning, a fantastic group of people, and they did a test flight for us on their balloon where we were able to test at least that the code worked, the autopilot could survive the temperatures, that the sensor data looked good, that the servos, didn't freeze up, that type of thing. So we had this little payload in a styrofoam box and the airspeed sensor sticking out on the left there, because the airspeed freezing up was a potential issue. And then that's the balloon launch on the bottom left corner there, and we ended up getting a good flight. So what you can see here is a bit of the data we got back from this flight, and I found the temperature data quite fascinating. Harks back to geography lessons in high school. So the red line there is our altitude above sea level. And you can see there we got up to about 31 kilometres above sea level, which is fairly high for an autopilot. But the yellow line is the external temperature. That's the temperature on the airspeed sensor, right? And you can see that started up. The right-hand axis is temperature. The left-hand axis is height in metres. And the horizontal axis is time. And you can see there that the balloon was steadily, the red line, the altitude rising. But the yellow line, the temperature decreases and decreases and decreases until it got to about minus 51, minus 52 degrees centigrade, so quite cold, but then the temperature starts rising again, which is the classic profile in the atmosphere, because you've got the troposphere that we live in, and then at around 20 kilometres or so, which is roughly where we saw it, you get the tropopause, and the temperature actually starts rising again as you get into the stratosphere. So this is then stratospheric flight, which is nice to see. You can also see the electronics temperature. The other temperatures are the temperature of the various sensors on board, the IMU temperatures and the barometric temperature, and they never got below zero. They never froze. So the electronics stayed sufficiently warm and things, which was good. So the other thing we were trying to test in this flight was the radio link. And because of course, code works first time, every time. Everyone knows that. So we should trust our code, but just in case, there may be a bug or two, we're going to have a telemetry link and be able to get live telemetry back to Australia, where I'll be sitting in my home in Australia, monitoring the telemetry in the flight, and being able to nudge the auto-tune algorithm as needed to try to get it to land at the right airport. And so the radio link was critical for that, and what you can see here is the distance from home, which got up to 35 kilometres as, line of sight. And you can see that the radio links, there was only a few dropouts in that flight. And the cause of them, see on the left there, the yellow line is the background noise in the aircraft. And it was great when it was first turned on, but then a few minutes after the whole system was first turned on, suddenly the noise rose quite considerably, from about an RSSI of 60 up to about an RSSI of 85 or 90. So a difference between 60 and 85, that's a 25 RSSI, which is about 12 dB. So we suddenly got 12 dB more noise from something else in the payload, because this wasn't an exclusive payload. So there was some other radio transmitter. And what we could see is that when we extrapolate out the potential range of this radio, we would have got 150, 200 kilometres with a one-way link, coming from the aircraft to the ground, because very low noise on the ground. The green line is the noise floor on the ground station. The yellow line is the noise floor in the aircraft. And it's really just reinforcing the old lesson of these types of radios, which is, the biggest limitation on your range is actually your noise floor, and trying to get rid of those noise sources. And so we had a severe noise source, RF noise source, at the 900 megahertz band, and that caused us to get a number of dropouts. It was still controllable the whole time, but we would like to get rid of that noise floor. So as I said, we were hoping to actually have done the mission by this conference, and that I was going to present the flight videos, etc. Instead, we've been waiting for permission from the FAA, because for some reason they are slightly sceptical about the mission, and it seems to be taking a while to get permission. So we have commemorative waiting for the FAA mugs for the mission, and we have this art of sitting around waiting for the FAA. So that's what it's generated so far, plus the test flights. But I hope that sometime in the next few months we'll get the go-ahead and do the mission and hopefully neatly land at Spaceport USA. Okay, so there's a lot of other development happening in the hardware area as well. There's been massive amounts of new autopilot boards in the last year, so it's a wonderful time to get into open source autopilots. So if you're on the edge and wondering, do I want to do open source autopilots? Yes, it's great fun. Flying robots, really, what could be better? So I was going to show you a few bits and pieces. There's this little one, which is actually the same sort of one that's the prize for the raffle, so you should go and enter the raffle. This actually runs Linux. This is called a Bebop. Runs Linux, and it now runs ArduPilot as well. We've been collaborating with the manufacturer, and so ArduPilot is an option, so you can run a full open source autopilot stack on this little Bebop, and it's a wonderful little computer. Fantastic work being done by the people at Parrot. There's also the bottom right there, the 3DR Solo. You can walk into Harvey Norman and buy one of those things in Australia, and it is running the open source ArduPilot autopilot, which is, it's fantastic that you just walk into a store like Harvey Norman and buy yourself a open source autopilot drone. Absolutely wonderful. Very, very capable system. It's got two computers, one running a Pixhawk 2, which is this one, and one running running Linux for the communication and the extra shots and that sort of thing. Another very interesting one lately is this one. This is the Qualcomm flight board, which is a Snapdragon CPU, and Qualcomm's pushing this quite hard as the future of autopilots. And it is a wonderful piece of hardware. 4 ARM Crate CPUs plus 3 DSPs. And the DSPs have a complete shared memory with the ARM CPUs. So all of the memory just shared, their own L1, L2 cache, but all the rest of memory shared. So we've got ArduPilot running on this, and it's good and bad. It's a marvelous piece of hardware, but the obvious place to run the autopilot is on the DSPs, which we can do. We have 2 ports, one running on Linux on the Crate CPUs, the ARM CPUs, and another port of ArduPilot running directly on the DSPs. Unfortunately, the DSPs run a proprietary RTOS called Quirt. And so, it's a little bit sad to think that we might be running on proprietary operating systems in future with these autopilots. But it is an incredibly capable piece of hardware with built-in 2 cameras, a 4K camera out the front there and a 640-480 camera below for doing optical flow, for positioning, like an optical mouse in the sky. If you want the pure open hardware, open software experience, then the one on the bottom left, the BBB Mini, is for you, which is a kit for the BeagleBone Black, a do-it-yourself kit for amazingly low money that provides a fantastically capable autopilot on top of the BeagleBone Black, utilising the programmable the PRUs, real-time units, for doing all the necessary real-time stuff. And another one is the NavIO 2 in the top right there, which is based on the Raspberry Pi 2. It's a cape for the Raspberry Pi 2 that also provides an incredibly capable autopilot. So it's a wonderful time to... Oh, the top left one, of course, is the PXF Mini, based on the Raspberry Pi Zero, which is a really, really compact autopilot. The Raspberry Pi Zero is tiny and makes for a great basis for an autopilot in smaller aircraft. All right, so it's a great time to get into free software autopilots. And I'd encourage you to go and have a look at our site, ardupilot.com, dronecode.org, which is a collaboration between a whole different lot of autopilot-related projects, and the Canberra UAV site, which is our particular group of crazy people doing our particular thing for the Outback Challenge. So, and I'd also like to mention, please donate to the Software Freedom Conservancy, a really good cause. So, if you're here and you care about software freedom, I'd encourage you to donate.